Land mass makes up about 29% of the Earth's surface area, but wind, as we know it, is a force that sweeps across the entire planet. So although landlocked turbines are currently harnessing enormous amounts of renewable energy, in truth, they're tapping into only a small fraction of what's available. But that's quickly changing. Let's take a look at how companies around the world are taking wind energy captured at sea and channeling it back to land and into our homes, and at how these marvelous machines are capable of much more than meets the eye. Offshore turbines are, from the waist up, practically identical to their counterparts on land, with one fairly obvious difference: they're typically bigger. The tallest onshore turbine in the US, for example, stands at a height of about 574 feet. The offshore Hallade X by GE, meanwhile, is a whopping 853 feet tall. That's nearly 3 times as tall as the Statue of Liberty. On top of that, the Hallade X boasts turbines approximately 1.5 times the wingspan of a Boeing 747. Despite the size disparity, the operating mechanism of turbines onshore and off are pretty much the same. The energy carried by wind turns 2 or 3 propeller-like blades around a rotor. That rotor then turns the main shaft. This low-speed shaft spins at the same speed as the blades, about 7 to 12 turns per minute. A gearbox boosts that speed by more than 100 times and transfers the energy to a high-speed shaft, now spinning at more than 1,500 revolutions per minute. The high-speed shaft transmits kinetic energy to a generator that converts it into electricity. A separate converter then turns the direct current fed into alternating current, and that current is then fed into a substation, the last stop that the wind-generated electricity makes at sea before it's distributed on land. Here's where things get interesting. Wind turbines are almost never built as standalone structures. They are built in arrays, called wind farms, to harvest as much energy as possible. But not all turbines on an offshore wind farm feed into a substation. Turbines are strung together in bundles of about 8. Cables running between turbines feed electrical energy from the outermost structure to the next innermost structure, then to the next, and the next, and the next, until all of that energy finally reaches the substation. The substation collects all the electricity shuttled through this energy brigade, and ultimately it exports it to the nearest onshore substation, which then delivers electricity to the electrical grid, and then to our homes. The substation, like the turbines that feed into them, are gigantic works of engineering themselves. Offshore wind substations can weigh up to 22,000 tons, and on paper, their specifications can read like those of a luxury beach hotel, complete with boat landings, full accommodation, and a helicopter deck. Installing these sea giants is understandably capital and energy intensive. The substations installed at the UK's London Array offshore wind farm, for example, required the use of a 3,300-ton lift capacity floating crane just to get them in place, 12 miles from shore. Fortunately, engineers have devised clever ways of cutting the cost of substation installation. One option is the self-installing platform. Platforms of this type are first floated into place. The platform legs are then lowered underwater until their can-shaped feet hit the seafloor. Using tremendous suction power, the feet dig into the seabed while the platform gently rests at the surface. Altogether, offshore wind farms are massive undertakings, both physically and financially. But precisely because of their size, many of these megastructures have the capacity to generate enough electricity to offset their cost of installation in as little as a few years, and they can be expected to operate reliably for up to 30 years. But generating electricity is only one of the benefits that offshore wind farms bring to the proverbial table. One unintended consequence of huddling enormous wind turbines along coastlines is shelter against hurricanes. Researchers from the University of Delaware and Stanford University have shown that offshore wind turbines might be capable of reducing hurricane wind speeds, wave heights, and storm surges that could otherwise lead to disastrous flooding. Their findings are the result of co-opting a computer model originally designed to study air pollution, energy, weather, and climate. That model had recently been used to explore two seemingly unrelated research questions. How do hurricanes develop? And how much energy can wind turbines extract from global wind currents? It seemed then only a matter of time before the next logical question was asked. What would happen if a hurricane encountered a large array of offshore wind turbines? To find out, the team fed their computer model data describing three real-life hurricanes: Hurricanes Sandy and Isaac, which struck New York and New Orleans in 2012, and Hurricane Katrina, which decimated New Orleans in 2005. The model generated some head-turning results. Offshore turbines, the team found, could diminish peak hurricane winds by up to 50% and storm surges by up to 79%. Those reductions were achieved by the turbine's ability to slow the outer rotation winds of the hurricanes. That reduced the wave height and, in turn, the movement of air toward the hurricane's center. In terms of real-world feasibility, however, hurricane stopping power might be harder to come by. The researchers' simulation assumed an array of 78,000 wind turbines. Even as offshore wind energy gains momentum, it isn't likely to support projects anywhere near that size in the near future. But the ability to lessen the effect of natural disasters, even by a fraction, could be enough to attract more interest in offshore wind. And hurricanes aren't the only disaster scenario where turbines could lend a helping hand. Geoscientists led by the California Institute of Technology are using fiber optic cables underneath wind farms to detect earthquakes. Offshore wind farms and substations must be connected to land to not only deliver energy, but also as a means of communication to exchange data, critical for smooth operation. That's why buried beneath most wind farms around the world, you'll find miles of fiber optic communications cables. But these cables can do more than shuttle information. Tiny imperfections in fiber optic cables can reflect back small amounts of light when shined with a laser. The defects serve as physical waypoints, which are useful for visualizing what's underground when exploring for oil and gas deposits. They're also good for detecting seismic activity. As the Earth moves through a seismic wave, these reference points shift slightly out of position. By measuring these shifts over time, scientists can, in principle, track the progression of that wave and thus the development of an earthquake. In August of 2018, the team was able to detect and record a magnitude 8.2 earthquake near Fiji using a network of fiber optic cables below an offshore wind farm in the North Sea. In doing so, the researchers demonstrated that instead of installing new and expensive seismometers underground, they could simply repurpose existing technology to fill the enormous blind spots in the global seismic network. Colossal, efficient, and surprisingly versatile, offshore wind turbines are incredible feats of engineering, and we have yet to witness their full potential. As fossil fuel reserves edge closer to their inevitable end amid a changing global climate, we could have a front-row seat to the action, with offshore wind poised to play a bigger role in renewable energy than ever before.